Well, thank you. It's a pleasure to be here today. And yesterday, I actually spoke to the group of undergraduate students, and I have to say, they spent considerably more time asking questions and getting responses than I actually lectured to them. So that turned out to probably be useful, even so. So today, what I'm going to talk about is this idea of really thinking scientifically based on research about how we go about teaching and learning these subjects. And this is relevant to both the teaching in class, but it's also relevant to training of graduate students and just individually how people can optimize their learning. Now, but before I get into those details, I'm going to just quickly give you a history of how I came to be where I am and thinking about this subject. When I was first teaching physics, I think I responded to just the same way that almost everyone does when they're asked to teach some subject. I would, was beginning physics at that point, and so I would go and think about the particular topic very carefully, get it figured out in my own mind very clearly, so that I could go and explain it to the students, expecting them to think about it the same way I did. But I've always believed in measuring things, whether it was in physics or with my teaching, and when I would actually probe in details to how the students were thinking, it was clear that my brilliantly clear explanations were leaving most of the students quite confused and baffled. And for many years, this just went on of something that didn't seem possible to do anything different, anything better. My other faculty colleagues, I tested their students, and the results were much the same. But where I became to understand this better and differently didn't actually come from my teaching in the classroom. It actually came from my work on doing research in atomic physics with graduate students. And it started with a basic puzzle about those research students, which is that they came to work in my research lab, and they didn't, in order to do that, they'd had many years of great success in their math and science courses. Otherwise, they didn't get to work in my lab. But in spite of all that success in courses, I found that when they started trying to actually do physics research, they couldn't do it very well at all. But after just a few years working in the research lab, they had become expert physicists. And so I saw this happen over and over, and I got more and more puzzled by this, particularly puzzled by the fact that the students who did the very best in their coursework and exams never turned out to be the best scientists. And so I eventually reached the point where deciding there was some fundamental scientific question here, and so I approached it like I did a scientific question. Well, first you make a hypothesis, and then you go out and look at the data to test that hypothesis. So my original hypothesis was the one that many faculty have seen with students, is that maybe students just have to see the material over many times and sort of go through the equivalent of a 17-year caterpillar stage before their brain can sort of transform into a physicist butterfly thinking about this. But I wasn't, so then I really got serious about looking at the research on how people learn, particularly how they learn physics. And I discovered there was research on that. And basically it said, no, this was not the right explanation. But it did completely explain this puzzle about how the students developed. It gave me a completely different way to think about teaching. And then most importantly, it really got me started doing science education research, where I could think about, I realized you could approach the teaching and learning of science in much the same way as I approach physics. You do controlled experiments, you compare, change different parameters, you measure the results, and you get data on what really works. And so for many, several decades, I've actually had two parallel research programs, one doing work with lasers and atoms, and one doing work on studying how students are learning science. And so I'm going to start out by showing you the kind of results you can get from these controlled experiments of comparing different ways of teaching science, and then I'll go into the underlying principles behind them. So this is an example where it was just measuring the learning that students get in a class, looking at a very large introductory physics course, and comparing two sections that we carefully measured of equivalent sets of students taught in the same class. And they were taught in two different ways, and then both given the same test right afterwards to see how much they'd learned. And the comparison here was between the one section was taught by someone who's a very experienced professor, highly rated by the students, but used the traditional lecture approach. And the other section was taught by new physics PhD, but trained in these, I'll call them scientific or research-based methods of teaching physics. And so when the two sections were then taught in this for a week, covering this material, and both tested, the results were that the traditional lecture class, this is the histogram, number of students versus their score on the test. The traditional class looks like this. The scientific teaching class looks like this. So these students who are clearly learning much more than from the students taught by the experienced professor here. And so, this is the way most science classes are being taught, and yet it's producing much less learning in this experiment. So, that raises the question, why does this happen? What can we understand this? And the rest of my talk is really about understanding why this result is quite predictable, actually. And it really, the reasons behind this really come from the fact that over the last few decades, there have been major advances in 3 different areas of research, but they're now coming together in a very nice, consistent way to give us a much better understanding about how to achieve learning of complex thinking like a physicist, the kind of things that was tested in that in the test those students got there. And these 3 areas of research are first cognitive psychology, that's people study in labs, how basic processes of how people think and learn, new brain research here, and then work in university science classrooms, the kind of research that I do. And although this work is really, we have data almost entirely just from science and engineering classrooms, the fact is that this work down here is quite general to broad areas of disciplines. And so it's very likely, in fact, you can make very strong arguments that everything I say about science and engineering can really be applied in most other university disciplines. I'll just mention, by the way, that in the cognitive psychology, there's actually been some quite important work in this in Japan. From the university science classrooms, there's been much less. Most of that work's been carried out in North America, but Professor Murata will tell us later today about studies they're just starting to do in Japanese classrooms that look astonishingly consistent with the data we're getting from other countries. And I think this is really a statement that this kind of transcends the local cultures and so on, and really that's really targeting the heart of thinking in scientific terms, which are actually quite general and international. So, okay, so now getting into the details of what I'm going to cover in my talk, I first want to talk in more detail about what it really means to think like a scientist and what I see as the educational goal of our courses. I want to emphasize this doesn't mean turning them all into scientists and engineers. We have many students of which it's very valuable. They take some science and engineering courses, even though they're going to go into a whole variety of different professions. And so what I really see as the important educational goal for these students is to learn to make better decisions. And what I mean by that is, in the relevant context, to use the reasoning and knowledge, the scientific reasoning and knowledge, to make choices and decisions that are improved by that way of thinking. And that's really what we want our students to come away with. It's not very important that they memorize some long list of, procedures and facts that don't really help them make choices. So after I talk more about exactly what this, or more about what this means, I'll talk about how this capability of, scientific decision-making, how that's learned. And then I'll go on, this is sort of really the cognitive psychology part. And then I'll show you the idea of how you can apply these in the university classroom and some of the data that we get from studies that do that. Okay, so let me start talking about what makes up expert thinking, the idea of how, say, scientists and engineers think that makes them unique as experts. And cognitive psychologists have studied this kind of expert thinking across a whole variety of different fields of chess players and doctors and scientists and historians and so on. And they find out that there's a few very consistent basic features that make up this kind of expert thinking. And there's a very consistent process of how those capabilities are developed. And so the first component of expert thinking is experts have a whole lot of knowledge in their subject. Everybody could guess that one. But the others aren't as obvious. The second is that experts in every field have a very particular way of organizing all their knowledge of the subject that makes it so they can retrieve and apply that information highly effectively when it's useful for solving some problem they face. And so, for example, when we talk about a scientific concept, it's really the way that experts in a field of science have taken a very large, different set of information and results and seen how they can organize that all together. And so when faced with a new problem, very quickly decide whether all that information is useful to solving the problem or not. And you actually go every field of engineering, every scholarly discipline, when you look carefully at it, has these very unique ways of fitting together all the work, structuring the knowledge of that discipline. The third basic component of expert thinking is the ability to monitor your own thinking and learning when working in the subject. And so, an expert in physics, for example, as they're working through a problem, they're able to monitor if this seems to be a good way and they're making progress, and then catch themselves if it doesn't seem to be going in the right direction, and stop and change and go on and take a different, more productive approach. This is something that we see consistently experts do, and people who are learning the subject who are non-experts consistently fail to make that recognition, will continue down an unsuccessful path much longer. So these three basic components of expert thinking here, the research shows they're fundamentally new ways of thinking. No one comes by these naturally. They're always and only developed by practicing, learning them by practicing. And it takes many hours of intense practice to develop these capabilities. And to reach a sort of, University of Tokyo professor high level of expertise, it consistently takes many thousands of hours, is what the research shows. And it's really very recently we're coming to recognize that requirement is basically a biological requirement. That in fact, what's happening here is through this intense practice for many hours, the brain is actually being changed. It's being rewired in a very substantial way. So the neuron connections and so on are actually changing in response to these demands to optimize the capabilities of that brain to solve these kinds of problems. And so it's really the fact that it takes a long time for the brain to make enough changes to reach the high level of expertise, but it's really in that changed brain that the expertise lies. And so to get the brain to make those kind of changes, it has to be exercised in the right way. And so we now realize that learning expertise is very much like building up a muscle. You have to use that particular muscle, and you have to use it very strenuously over a long period of time. And in response, the body says, okay, it's going to be all those demands. I'm going to make that muscle bigger and stronger. It does much the same thing to intense, strenuous demands on the brain over a long period of time. So those demands, though, have to involve just the kind of tasks and thinking that the brain needs to get better at. And so it's got to be practicing the particular thinking skills you need to learn. And in addition, it's not just enough to practice, as everyone knows who tried to learn something. You have to practice it, and then you have to get feedback on how well you were doing and how you could do better to improve. And that's basically what's exactly needed for this learning expertise, learning to think like an expert scientist or engineer. So that's quite general. I want to now try and give you a little better idea of what some of the kinds of thinking practice that you need to become an expert scientist or engineer. First is within the field you want to become an expert, experts have a particular set of conceptual or mental models they use for figuring things out. And more importantly, they've got a very specific set of criteria for deciding if a problem looks like this, which of these conceptual models is going to be applicable there and which are not, and why. Second, they've got complex pattern recognition systems that they can look at a problem and quickly sort out from all this information you have which things are relevant to solving the problem and which can be ignored because they're not important. They have ways when they get a conclusion or an answer, they've got very specific criteria for checking if that answer makes sense, is likely correct or not. And then finally, another very general feature is every discipline has particular specialized ways to to represent information, whether it's, complicated specialized figures or graphs, equations, etc. And so experts move between these different representations and use that to get new insights and new ideas for solving problems. Okay, so I could go on, but these are some of the main ones. And so doing these sorts of things are exactly what you need to be practicing and getting feedback on if you're going to develop expertise. Now, if you stop to think about this, you should be struck by the fact that I don't list any particular topics here because I'm sure it's quite universal in higher education that most of the discussions about education and math, any field of science or engineering, are about which topics are we going to cover and then have the students learn and in which order and so on. But the point that's really important is, okay, the knowledge and topics are important, but they're really only meaningful if they're integrated in with these broader aspects of expert thinking, because it's these that really tell the learner when and how to use that knowledge to be effective. And we have lots and lots of examples from research where students will know a bunch of facts and information, but when faced with a problem, never realize whether that information is relevant or not and what information they should use. So it's really the integrated whole that really has to go into the practice and the learning here. So if you think about that's what the learner has to be doing to become an expert, well, what's the teacher need to be doing? Well, what makes an effective teacher then is someone who thinks about designing the proper practice tasks that target the expert thinking you want the learner to use, and at the right level of difficulty. They're challenging but not impossible for the learner given their backgrounds, and then provides this useful guiding feedback as the learners work through these tasks to help them get better. And then finally is providing the motivation, the rationale for the learners to why they should put in the inherently intense effort required, hard work needed to actually learn any serious subject. So when you think about what goes into this, you realize this is exactly what a good athletic coach does in some particular sport, whether it's learning to teach someone to become an ice skater, for example. They're thinking of the right practice, they're giving feedback, and they're motivating. So I kind of think the best way to think about what makes an effective teacher is really somebody who's a cognitive equivalent to a good athletic coach. Now, it's also true that if you think about what's needed there to do these things well, you realize that these really demand that the teacher has a very high level of content mastery. They have to really understand in depth what expert thinking is in the field, then if they're really going to be able to do these tasks properly. And so I actually think this is the real ultimate justification for the research university like University of Tokyo, where you have the people who are the most experts in the field actually, are being called upon to teach the subjects. But it is important to realize, and that's what research is telling us very clearly now, it's necessary to have a mastery of content. It's not sufficient. You also have to have expertise in teaching to know how to effectively transfer that expertise to the students. So before I give you examples of actually how this can be done, I want to explain a little more about what I mean by this kind of expert practice with feedback teaching by explaining what it's not. Because many times I'll give this talk and people will say things like, oh, you just mean that's like hands-on learning, or these days, that's just a flipped classroom. And I want to emphasize that the difference here, because it's not those. And the reason it's not is these kinds of things, they're just focusing on sort of what the learner, what activities they're doing and where they're doing it. They're not focusing on what the learner's actually thinking. And that's really the key aspect of this, is it's really focused on exactly what the thinking process the learner's involved with and supporting that. And so these kind of things, like the flipped classroom, they might involve the proper cognitive tasks for the learners, but oftentimes they don't, because it's not really a core idea. Okay, so let me move on to tell you how these ideas can really be applied in the classroom of this practicing thinking like a scientist with getting feedback on it. And I'm going to give you I'm going to illustrate this in the example of a very large classroom in introductory physics with hundreds of students, because for most people, it's a little harder to understand how to do that than if I had 10 or 20 students at a time. But as I'll show you, we have good data showing it really can be done quite effectively in this large classroom environment. So, okay, so how would I do this? I'm imagining I'm going to teach a room this size full of students here. Basic ideas of electricity, current and voltage covered in, first year physics, undergraduate physics. So first, I would have all you students. I'd give you a short targeted reading assignment, and I'd have a little online quiz to you test to show that you really did it, give you a little reward for it. Now, I don't really expect you to learn the subject, not to learn to think like an expert about the subject from just reading it in a textbook. That's just too hard for most students. But what I do expect you to get out of this is that the basic information, the facts and terminology, those are things you can very easily get from a book, and then I don't have to waste valuable class time with this simple information transfer. So then I don't have to tell you stuff. I can start class with questions or problems you have to solve. So for example, I would start the class on this with this, give you this case of a circuit with light bulbs here and a battery, and ask you to predict what's going to happen to the brightness of that switch, brightness of this bulb when I close this switch. And each of you would have a personal response system, and there's, nowadays, oftentimes people just use cell phones for this. I think we'll be getting an example in the panel discussion where you can do this. And so that every individual student in the class would have to answer, and my computer would record who they were and what answer they chose. Now, from an instructor perspective, I can be looking at the input here. It's clearly useful to know if many students get this right or many students get it wrong. But from a learning perspective, actually, the more important thing is what this does to the students' thinking. And it's the fact that they have to commit to some answer that they have some accountability for. So even though most of these questions count very little or nothing in the grades, the fact is they know I can look in there and see who they, what answer they chose, and that level just causes people to think much more intently about any question you give them and primes them much better to learn from the subsequent activities, which in this case, what I would do is I wouldn't show them the answer, I wouldn't show them the vote, because we tested how to do this right. I would then call on them, and each student would be part of a consensus group, and I'd call on them to talk to each other, decide on the correct answer and the reasons for it, and they'd re-vote. And while they're doing that discussion, then I would be wandering up and down the aisles, listening in on these conversations, getting a little image of what's going on in those students' brains from hearing what they're talking about. What aspects are they using correct physics reasoning, and what aspects are they confused about and thinking about it incorrectly? And it turns out that if you haven't taught this way, you may wonder how well you can tell the whole, in a big class like this. And I can just tell you from our data that, just running around the aisles here quickly, I can quite easily capture, 80 or 90% of what people are thinking, because there's just not that much variation across the different ideas. So if you just do little sampling the edges, you got a pretty clear idea. Then the students have talked, re-voted, then I'd go ahead and that would take a few minutes. Then I would demonstrate the result of what actually happens. I would show the results from the votes. And then most importantly, I would then have a follow-up summary discussion. And during that discussion, I would bring out all of the correct and incorrect reasoning that students were using to solve this problem, and talk about why it was correct. But then, most importantly, I would talk about which reasoning was incorrect and why. And this is something I've learned a lot from the cognitive psychologists from, is that it's when you really are learning something and making progress, it's when you come to understand, not just if you did something right or wrong, but when you did it wrong, what was incorrect about your thinking and how to change that thinking to solve future problems better, to be able to master the subject more. Okay, so that's the way the process would work. This might take 10 minutes to run through that with all the follow-up student questions that actually probe this subject and cover additional material. But if you get back to my original purpose here, how are the students practicing thinking like physicists? Well, you can see that first they've got a new situation. They have to decide what's important and what isn't. Then they have to think about, okay, formulate really their concept of how electricity works and how it affects light bulbs. And then they've got to test that reasoning both in the discussions with other students and in seeing how their predictions compare with what actually happens. And so very much the same basic ideas of formulating concepts, testing, and applying concepts. That's the heart of scientific reasoning. And while they're doing that, they're getting multiple forms of feedback to help them improve their thinking. They're getting feedback from their discussions with their fellow students and listening to their fellow students' arguments. They're getting it they're comparing with what actually is observed. And finally, they're getting the feedback from now me, the highly informed instructor, who can very specifically target the issues that they're struggling with. So that's basically how you can implement this in a classroom of up to a few hundred students effectively. So I'm now going to move on to some of the studies and evidence we have when you put these principles in play in classroom activities. A few years ago, started making a count, and I came up with something around 1,000 studies that across different fields of science and engineering that had compared this kind of scientific teaching with the results of the traditional lecture. And what one sees from those comparisons is consistently greater learning by the students, particularly when tested on things like how much can they make decisions like an expert or predict new things in a situation like an expert scientist or engineer. They have lower failure rates, so greater success rates in courses, and they benefit all students, but there seems to be usually added benefit for the students who are kind of most at the borderline, most at risk in these cases. And so I'm going to show you a few examples of these, my sort of favorite studies. This one's from teaching introductory physics, and it's looking at sort of the beginning mechanics course that is pretty much covers the same ideas of force and motion every place in the world when this class is taught. And in this, and we have some rather well-developed tests, and actually you'll hear later at the panel about some of these that physicists have developed that really test how well students can use these concepts of force and motion like a physicist does when they're faced with to make predictions of what's going to happen in some simple real-world situation they haven't seen before, like cars running into trucks, etc. And so using this test in this particular study, they had many different instructors who taught this in many relatively small sections. This is University of California State at San Luis Obispo. And they collected data across these different instructors, and they came out consistently over many years with a learning gain of about 0.3. That's just the fraction the students learned because they didn't know at the beginning. And this turns out, we have data from undergraduate physics at many different places, and this turns out to be a typical score for a well-taught lecture-based course. And then in this study, they had all these instructors switch to this different way of teaching where the students, at 40 per room, were sitting around at tables like this. They were given a well-designed set of problems to work through together while the instructor circulated around and acted as a coach as they worked through these structured problems. And then at the end of the semester, they gave the students the same test of conceptual understanding, and basically all of the instructors improved, and the average now is just twice the learning that they had with the traditional teaching method. And so it's important to emphasize here, you have the same people, you have the same instructors. They simply learn to use better teaching methods, and their students are learning much more. I mean, just how much more? You can see this instructor is really quite amazing that their students are now learning a factor of 6 better conceptual mastery than they were getting when they were using less effective teaching methods. Here's a different subject, different level. This is Beth Simon. She's at University of California, San Diego in computer science. She came and worked with me for a year, learned how to teach these methods that I illustrated with the electricity example, went back to the other 3 professors who taught the core computer science courses at UC San Diego, implemented this way of teaching there, and they looked at the drop and failure rates from those courses and saw that they went down dramatically across all of them. And so what they now have this situation that as they've adopted this different sort of research-based approach to teaching, they're getting about 1/3 the failure rate that they used to have. This means they have a very large number of students who are now able to successfully get degrees in computer science at UCSD because their faculty are teaching more effectively. So those examples and the great majority of the work in this field are all based on looking over an entire course, entire term, and the learning that takes place. That involves not just what happens in the classroom, but studying for homework and exams and so on outside of class. And so we did this study, which was to focus only on the learning that takes place in the classroom. So this is just a research study, and we did that because first we were interested in measuring it because most faculty and professors focus primarily on just what's going on in the classroom. But the second, we wanted to address a concern that's very often raised when people hear about this teaching method is, how can you cover as much material? And so we wanted to cover exactly the same material or try to in 2 different methods and then measure the learning. And so this, as I said earlier, took 2 identical sections, or the students were very nearly identical, from a big introductory college physics course, 270 students each. I'll remind you, the control section was the standard way this is taught by somebody who was considered, ranked by the students as a good teacher, very experienced. And the experimental section was someone who'd been through my training program on using this research-based teaching methods. And these 2 instructors agreed to cover the same set of learning objectives, so exactly the same content, to be covered in exactly 1 week so 3 hours of lectures in 1 week. And then they had a jointly prepared exam that tested just exactly the objectives they gave. And this was given to the students sort of as a surprise at the start of the next class, so they weren't home studying for it and so on. So it was really probing just what they got from being in class. And the experimental class section had exactly the same things I've already talked about, little short readings ahead of time, and then during class they were solving questions, answering with a response system, or sometimes this was more mathematical, so they'd be worksheets where they'd be writing things down, calculating, again, working together, talking to each other. And the instructor, I want to emphasize when you're teaching this way, it's not as if the instructors aren't talking. When we see a well-run class like this, half the time is still spent with the instructors talking, but rather than the talking being telling students they don't have a reason to know why it's interesting or useful, it's all follow-up discussion when the students have been working and thinking about something, answering their questions and providing follow-up guidance. And that's what produced this histograms that I showed before. I want to say a couple more things about this. First, just random guessing on this particular test would give you student 3. So you sort of have, the amount of learning is really how high above 3 they are on it. And if you look at it that way, you can realize just what an enormous difference there is between the learning in this case and the learning in that case. The other point I want to emphasize is that you can see the entire distributions moved up. The reason that's important is very often when people hear about these new teaching methods, they always ask, well, maybe this just benefits the weaker students. Occasionally someone will think it benefits the stronger students. But what this data and other data I could show you that looks similar is this benefits all the students. This is just the way the human brain learns, and so teaching this way, you get the whole distribution moving up. We also measured engagement, the sort of technical how we do that, but not surprising, these students, the engagement's much higher because they're being called upon to answer questions, to provide answers, justify reasoning, et cetera, all the time. Whereas these students, they're just sitting there listening. Okay, so those are some examples from a lot of introductory science courses and of different sizes, and most of the education research has happened for those settings. But more recently, my own group in particular has been looking at using these ideas and testing them in more advanced level courses. And so we've been looking actually at the second up through fourth year physics courses across both University of British Columbia and also Stanford, and putting these same basic principles into practice. These are smaller course classes, as you can see, but the students are, again, working away as the instructors are going around sort of acting as coaches. And so I don't need to go through these details again. The same principles are applying here. They get basic information outside of class, and then in class they're working through solving carefully structured and planned sets of problems they're working on. The instructor is guiding, providing regular feedback, pulling everybody together about every 10 minutes to make sure nobody gets lost and is moving along together. And we've got data showing that teaching this way, okay, and this is one particular fourth year course, but they've got about one full standard deviation improvement on some particularly challenging and authentic exam questions that were repeated. At Stanford, just in the last year and a half, we've actually had a large number of the courses taken by physics majors have been converted to this scientific teaching method involving quite a number of faculty there. And we've seen some kind of interesting results. First, attendance isn't required at Stanford, and so many students don't go to class, but we've seen the number of students coming to class has jumped up dramatically for all of these courses. And it's clearly because the students just see this as a much more effective learning activity, and so they want to come take advantage of it. The faculty have all found they're covering as much or more material when teaching this way. And when we look at the student responses, we collected anonymous feedback from essentially all the students in 3 of these courses on the teaching methods. And basically, they're extremely positive. They're overwhelmingly positive. Most of the students are arguing, campaigning that get all the physics courses taught this way because they see this as so much more effective than the lecture courses they were getting before. And finally, it's worth noting that the faculty actually have found they really prefer teaching this way. You know, they all say it does take some time to learn, and we've collected data from across the institutions where we've worked that it's something like an extra 50 hours of faculty time to develop the expertise to teach this way if you're not familiar with it. But we sort of supported the faculty to do this, and after they all say this is a much more rewarding way to teach. They feel the students are much more deeply engaged in the subject, and they as faculty are calling much more upon their expertise in the subject and transferring it more effectively to students. So they just like teaching that way better, and they all say they'll never go back to lecturing. And this is actually a typical faculty response we've seen from across about 200 faculty that we've had transform in how they teach science, faculty members, how they teach science, for the programs that ran at both University of British Columbia and University of Colorado. So let me just wrap up here. I mean, we've got something where the data says it's much better for the students learning, and the faculty like it better once they learn to teach that way. Why is the world filled with classes not being taught this way? And that really gets into issues of institutions and how institutions are organized and changed. And so I'm not going to go into that for this audience. I will say that we did, my wife Sarah Gilbert and I, launched this very large experiment at University of British Columbia, where we did show you can get entire departments to change their teaching and everybody wins. But it's complicated to do that, and there's a whole bunch of factors that come into it. And basically, I have a book written up on this that is coming out. If you want to learn more about this, you can go read all that. A whole bunch of things are important, but the most important is really the incentive system, that if we want faculty to adopt these methods, we have to, institutions have to find a way to evaluate teaching that captures whether these methods are really being used in a reasonable way and incentivize, reward faculty for teaching that. And once they start doing that, then faculty will adopt them. So, so just to finish up and have reasonable time for questions, I want to argue that really the real goal of a good science education should be to have the students learn to make decisions or choices based on the scientific reasoning and facts. And that learning comes from practicing that thinking by getting feedback. The research is overwhelming, showing that matters. And if one puts these practices into effect, you clearly improve the student both learning and enjoyment as well as faculty. And I think that we now have this very large body of research showing the effectiveness of this approach. And so my slides will be available, and if you want to learn more about this and these ideas, basically here's some good books to read, and lots of these sort of cover the basic principles of learning and teaching, and then at this website we have a lot of details about particular implementations of things in the classroom. So thank you.